Good morning, students. We are continuing with Biot Savart'S law that we had started with in the last chapter. To let us revise what Biot Savart'S law is in brief. The law stated that the magnetic field intensity dB due to a current element is proportional to four factors. The four factors were the current flowing through the current carrying conductor, the length of the current element, that is dl, and sine of the angle between the current element and the vector joining the current element and the point where you are finding out the value of b, and inversely proportional to the square of the distance between the current element and the point P. Yes, if you remember, we had done this in the last class, and after removing the sign of proportionality, the constant that we had was mu naught by 4 pi, and we had done one application of this Biot-Savart's law. The application was to find out the magnetic field due to a straight wire that was carrying current. If you remember, we had drawn a long straight wire and we had chosen a point P, and the current element was somewhere here, the length of which was dl, the vector joining this one, okay, and then we had drawn a perpendicular line like this angle was equal to phi, yes, this was equal to theta, phi plus theta is equal to 90 degree. After doing all the derivations, the final term that you had calculated was b is equal to mu naught by 4 pi I by a sin phi 1 plus sin phi 2. I had given you some assignment also to do, hope you have done it, okay. I have got a few responses so far. I expect everyone to please send your answers to me. Now, we are proceeding to the next application of Biot-Savart's law. The next application is to find B, means magnetic field intensity, at the center of a coil carrying current. The diagram will be very simple for you. You have a circular coil like this, okay. So, if you just connect it to a source of electricity, that is a battery, current will start flowing like this. So, here the value is I, the current is I, to which the value of B is directly proportional, yes, and at the center of a coil carrying current. So, if the center is O, we need to find out the magnetic field intensity B at the point O because of this coil that is carrying current. Okay, let's start with the derivation now. Let us consider a circular coil which is carrying current of radius r. Okay, this also happens to be our position vector between my current element dl. I am taking a small current element somewhere here, looks like a tangent to this circle, right, and this is the radius. So, the angle between this and this r and dl will be equal to 90 degree. This will be helpful when we later find out the expression, okay. Now, let I be the current flowing through the coil. You must be having the notes. Please keep it in front of you and just try to refer the notes, alright. Now, suppose the current, the coil is made of a large number of current elements, each of length dl. So, like here we have one dl, one more dl is here. So many dls are making up the entire length of the coil, and each of length dl. Now, according to Biot-Savart's law, the magnetic field intensity at the center O due to this current element IDL, in the last class I told you dl is the length and the current element is named as IDL, is given by, I will straight away write the scalar form, dB is equal to mu naught by 4 pi IDL sin theta by r square, and this theta, again I am repeating for you, it is the angle between dl and this position vector r, okay. Now, it is evident from the diagram that my theta is equal to 90 degree, So my next line expression will come out to be mu naught by 4 pi I dl sine 90, which is equal to 1 divided by r square. So this is the value of dB at the center of the current carrying coil. Okay. Now what about the direction of this dB? Because it is a vector, here I have written down the magnitude of which, and in the next line you should also write what is the direction of dB. The direction of dB is perpendicular to the plane of the loop that is carrying current. Okay, like I have told in the last class, the direction follows the vector rule to find out the direction. So it will be in a plane perpendicular to the plane containing this. Suppose this plane is the plane of the paper that you are using. The perpendicular plane will be either coming out or either going inside. In our case, it will be going inside, because if you tighten the screw from DL to R, the screw would be going inside. Okay. So don't forget to mention the direction after you find out the magnitude. This is just the magnitude, and you are required to write the direction of dB is in the plane perpendicular to the plane carrying this current. Okay. Now this is only the magnetic field intensity due to a small current element dl. Alright, but we don't have only one small portion here, we have the entire coil which is carrying current, which is contributing to the magnetic field at this point O. So what will be the total magnetic field? It will be equal to B is equal to integration dB. I hope you are getting it. Now just integrate this value here, copy the expression. I need not integrate mu naught by 4 pi, it is a constant. I also will be a constant, okay, by r square also does not change because this is the radius of the wire. Only thing you need to integrate is dl. Now dl means I am adding up this small length so many times. If I add up this dl infinite number of times, what I will be getting? I will be getting the entire length of this wire, which has been turned to be made into a circular loop, and the length of a circular loop is nothing but the circumference of the circular loop, whose formula is circumference is equal to 2 pi into r. So what will be the integration of dl? It will be the length of this circular loop, that is equal to the circumference, that is equal to 2 pi r. So I can write it here. The value of B is equal to mu naught by 4 pi I by r square, integration dl is nothing but 2 pi into r. Okay. So my final value will be equal to r can be cancelled, mu naught by 4 pi 2 pi I divided by r. See, here also these two terms can be cancelled, but I am not doing that because this constant has got a particular value. If we cancel this, this will no more remain mu naught by 4 pi. That's why I am not cancelling this out. Okay. So writing it in definite terms, mu naught by 4 pi 2 pi I into r. This is about one turn of the wire. If the wire has got just one turn, it will be 2 pi into I. But what if it has got n number of turns? One turn carries current I. If it has got 2 turns, it will be carrying the current equal to 2I. If it has got 3 turns, it will be carrying the current equal to 3I. If it is n number of turns, the total current will be equal to n into I. So the value of B will be equal to mu naught by 4 pi 2 pi Ni is divided by R, where N is the total number of turns of the loop, because if you integrate dl for n number of times, it will be 2 pi R n times. The total length will not be one time, it will be n times. Okay. So this is the total magnetic field intensity at the point O, that is the center of a circular loop which has got n number of turns in it. I hope it is clear. Now let's proceed to the third application, the last one in your syllabus. In fact, this becomes number 3. To find B on the axis. Okay? To find B at any point, suppose you have a circular coil like this in this plane. Okay? Now I am changing the plane. So it is kept like this, perpendicular to the plane of the board, and you want to calculate magnetic field intensity at any point P situated at a distance, say x. Alright, and here I will consider A as the radius of the coil that I am taking into consideration. Suppose the direction of flow of current is like this, magnitude of the current is I, okay, and I will be taking pair of diametrically opposite points as current elements. It means that this is the diameter, right? So if you have one diameter, 2 points lying on the opposite ends of the diameter, okay, each of length dl each, here also dl, okay, and I will be joining this dl at C. I name it these 2 points as C and D, okay. The position vector, say this is R, this also equal to say R dash, okay. Later on we will find out that R and R dash are equal, okay. Now we are going to find out the magnetic field intensity at a point P which is situated on the axis of a circular coil which is carrying current. I will name the central point as O. Alright. Now what is the value of R? Let's find out first. Looks like it is following Pythagoras theorem. It is a right angle triangle. So R will be equal to under root A square plus X square. Here also it is symmetrical. This one is also equal to A. So here also this R will be equal to under root A, R dash will be equal to under root A square plus X square, which means R and R dash are the same. Okay. Now these two angles also will be equal because all the lengths are equal. So angle there is phi. Okay. Now according to Biot Savart'S law, magnetic field at P due to the current element IDL at C is given by same formula. dB is equal to mu naught by 4 pi IDL sin theta by R square. Okay. Again in our case, if you look at this plane and this is in another plane, they are perpendicular planes. So this theta will be equal to 90. So dB will just come down to mu naught by 4 pi IDL by R was under root A square plus X square, square of which will be equal to A square plus X square. So this is dB at P due to the current element situated at the point C. Let us take this as equation 1. Now the magnetic field intensity at P due to the current element situated at D, which is just opposite to this C. So the current element IDL at D will be giving you a magnetic field intensity equal to, again same method, okay, say it is dB dash mu naught by 4 pi I dl, okay, divided by A square plus X square, again same method. Okay. Now this is equation 2. Now what about the directions of this dB and dB dash? Okay, I am not writing dB For this one also, because the magnitude may be the same but the direction is not the same. Alright, that's why I am not writing dB for both. Now we will talk about the direction of dB and dB dash. Now dB is directed to a plane, again a plane which is perpendicular to the plane containing DL and R. Alright, say the plane is directed here, okay. The name is, this point is E. So it is directed towards a plane that is perpendicular to CP. So the name of this plane is PE, alright. And what about dB dash? It is directed towards a plane that is perpendicular to DP, okay. Say the direction is somewhere here. I'll name it as F. So dB is directed towards PE and dB dash is directed towards PF, okay. Now I can resolve this dB. Now this is dB. Mind you, it is a 3-dimensional figure, so to get a clear picture you should be using a 3D space, alright. And this is my dB dash. Of course I have to put a vector sign, the directions are different for these two. Now dB and dB dash can be resolved into their mutually perpendicular rectangular components. I will just extend this line a bit, okay. Now the two components for dB will be this one and this will be equal to phi. This will be named as dB cos phi, and for this one another one rectangular components, this will be dB sin phi, and for dB dash one component will be this one because this angle is also equal to phi. So this is named dB cos phi and the other one will be overlapping on this one. So this is one more this is dB dash sin phi. You can see these two, dB the magnitude is equal, cos phi also will be equal, they are directed opposite to each other. They will cancel out each other. So this cos component will not be contributing to the magnetic field because of these 2 points. The only component that will be contributing will be dB sin phi and dB dash sin phi. So the magnetic field will be only because of this dB sin phi added up as many times as you have the number of opposite points. Like we have CD here, I might have AB situated diametrically opposite, because of which it will be dB sin phi again. Again I may have 2 more elements opposite to each other, that also will contribute to dB sin phi. So dB sin phi has to be integrated if you want to find the total magnetic field intensity because of the circular loop at a point P on the axis of the circular loop. So the total magnetic field induction at P due to the current through the entire coil is given by B will be integration dB, not dB, it is the component that is dB sin phi. That means the sine component of dB will be contributing to the magnetic field. Yes. Now what is dB? Mu naught by 4 pi I dl divided by r square was a square plus x square, alright, and sin phi for now I will write it as it is equal to mu naught by 4 pi, of course it is integration of this one, mu naught by 4 pi I by a square plus x square will come out of the integration. Even phi is a constant, so sin phi can be taken out. Only thing that has to be integrated is dl. Now again it is a circular loop. If you integrate dl many number of times, you will be getting the entire length of the coil. So it will be equal to mu naught by 4 pi I by a square plus x square. Now sin phi, if you take that triangle, any of the triangle, this one, okay, sin phi will be equal to a, that is perpendicular, by under root a square plus x square. Using the formula sin theta is equal to perpendicular by hypotenuse. The perpendicular is a and the hypotenuse is r, that is nothing but under root a square plus x square. Okay. Integration dl will be equal to 2 pi into a. Here my radius is a. Then mu naught by 4 pi, b is equal to mu naught by 4 pi I by, this is to the power 1, this is to the power half. So 1 plus half is equal to 3 by 2. So I can write it as a square plus x square 3 by 2. Okay. A is already there. 2 pi into a, the integration of dl. Okay. If I write it in simplified expression, mu naught by 4 pi, you will be getting 2 pi a square I divided by a square plus x square. Okay, this is for one turn. If you take n number of turns, integration dl will be 2 pi a into n. So for n number of turns, the expression will come out to be mu naught by 4 pi 2 pi n a square I by a square plus x square. This is raised to the power 3 by 2. This is the magnetic field intensity at any point on the axis due to a circular coil carrying current. Here we have taken small elements diametrically opposite to each other and the component was found out to be dB sin phi. We integrated dB sin phi to come to this expression. And after you finish this one, I have given you assignment. Okay, have a look at the assignment. It is just the application. I have given you hint also. Please do the assignments. Okay, thank you.